The second problem we'll take a look at involves what are called combinations, where we're going to be picking different teams. First of all, what is a combination? Well, a combination is basically a selection of things where the order doesn't matter. So this is kind of like the permutations that we talked about in our anagram example in the other lecture, but the difference here is order does not matter, whereas with permutations, order does matter. So here, let's just do an example. Let's say we have a group of mountain climbers, and we're just going to call them A, B, C, D, and E. And we want to do is we want to pick 3 of these members to scale a mountain. But we don't know if these team members will actually get along with each other. They might not. So what we want to do is take a look at all possible teams. So we want to look at all combinations of 3 climbers. So what would be those combinations? Well, here we would have ABC, ABD, ABE, and then ACD, ACE, and then ADE, and then BCD, BCE, BDE, and CDE. So these are all the different ways that we can pick 3 climbers where the order does not matter. Now, there is a very nice recursive solution for this problem. And the idea is that we're going to divide these combinations into 2 groups. Now, we're going to use our earlier example to help us with it. But the first group will be those groups, those combinations that begin with person A. And then the second group will be those combinations that don't begin with person A. Let's say N is the size of the group and K is the size of the team that we want to pick. So we're going to let NK in parentheses be the actual combinations of selecting K people from a group of N. So we're actually going to say NK is the complete list of combinations. And what we find is that in order to get NK, we can actually break it up into the 2 groups that we've mentioned. So one group is going to be N-1, K-1. So that's going to give us a list of combinations. And then we can include the N-1 K list of combinations. So if we put these 2 combinations of groups together, that would give us the full list of combinations. So in our earlier example, we were trying to pick 3 people out of 5. So that was the list of combinations for 5, 3. But what we find is we just combine the following 2 different groups. One where we're picking 2 people from a group of 4, and then another one where we're picking 3 people from a group of 4. So all we're doing here is just we're going to be selecting twice from a group of 4 in order to get our combinations of 3 people out of 5. So the first one was we're going to find all the ways to select 2 people from a group of 4. And then the second approach, or the second selection, is to find all the ways to select 3 people from a group of 4. So what are the different ways that we can actually select 2 people from a group of 4? And here we're just going to assume that we're not dealing with person A. We're going to deal with B, C, D, and E. So those different ways end up being BC, BD, BE, CD, CE, and DE. Now here's the trick. We're going to add person A to each of these combinations. And that would give us all the different combinations with A being one of the 3 people in the group. So that would give us ABC, ABD, ABE, ACD, ACE, and ADE. So that gives us that group. We mentioned earlier of our 2 groups, one of them being all the people with A. This is how we get it. Now, how do we get the other group, where all the group with 3 people without A? Well, that's the ways to select 3 people from a group of 4 without A. So that's going to give us BCD, BCE, BDE, and CDE. And what we find is when we combine these 2 sets, that gives us all the different ways of picking 3 people out of a group of 5. What we find is we can actually apply the same decomposition process to deal with the groups of 4. So for example, if we want to find all the people where all the combinations of picking 2 people from a group of 4, well, the way we do that is we would find all the different ways of picking 1 person from a group of 3, and then we include all the different ways of picking 2 people from a group of 3. And we see that we can just use recursion for this. And we can keep decomposing this further and further until the number of groups becomes very trivial and the actual combinations of groups is trivial. So what would be the base cases here? Well, these would be the combinations that make no sense. So that would be like if we get a 0 for either number, so if ends up being 0 or k ends up being 0, because it's kind of hard to pick 0 people from a group of 5 or pick 3 people from a group of 0. And also there's cases where the team size is greater than the group size. So we can't pick 3 people from a group of 2. That just doesn't work. Now something like 1-1 is valid. Picking one person from a group of 1, you just pick that one person, but there's no point in trying to break it down any further. So in these particular cases, we would just return. Now, how would we go about recording all the combinations? Well, what we can do is we just display them as we go along. So we don't actually display anything when we do a left recursive call. So remember, we have 2 different recursive calls. We don't display anything when we do the left one. However, whenever we make the second recursive call, that is when we're going to check our sequence. And what we would check to see is if adding one member would complete the team, then we would add the member and display the complete team. So what we're saying here is we do the left recursive call and get all those combinations. And then as we get to the second recursive call, we'll check if adding one member completes the team, then we'll go ahead and add a member and display that particular team.